I'm going to answer or get you started on section, oh, what was it? It was number 13 from section 5.3. First, I want to show you what my comments were in my lecture notebook for the videos following note number 128. For 128A, I summarized the situation where we had rotation about the y-axis. I drew my pictures and I set up my integral, and you'll notice that in this situation we are finding the height of the function by taking the upper x value minus the lower x function. I should say x function. Y is a function of x. Y is a function of x. Upper y function minus lower y function. But the lower y function here is simple. It's just y equals 0 because it's sitting on top of the x-axis. For video number 128b, we did a very similar thing because we were rotating about the same axis, the y-axis. But now it's a little more interesting because we have the height of the cylinder, of the shell, being the upper y minus the lower y, just like we did in 128a, except now the lower y function is not y equals 0, it's y equals x cubed. And then for video example 128c, we were now rotating about the x-axis instead of the y-axis, so the height was the rightmost x function minus the leftmost x function. And the other thing that changed was the radius. The radius in the previous two examples were x, while the radius here is going to be y. And in the last one, we have rotation about a line that's not either the axis. It's actually the vertical line, x equals 2. So that affects two different things. First of all, it changes the radius of our shell in the cloud. The radius is not x like it normally would be for rotation about vertical axis. Instead, it is 2 minus x, and you can see that when you look at the sketch on the xy axis, that's a distance from the distance between the center of the approximating rectangle and the axis of rotation. And there's also variation in the height of the function, but it's very similar to 128c, no, I should say 128b, in that the height of the function is the upper function, the y upper function minus the y lower function. So keeping that in mind, let's go to the problem at hand, the problem that we're working on, and see which one of these different scenarios that one fits into. Okay, let me resize the screen here, and we'll discuss this example. Well, we'll get it started anyway. In this example, we're asked to find the volume of the solid from rotating about the x-axis. Okay, so that tells you which one of those to look at in the previous comment note. We're going to rotate about the x-axis, the region obtained with the boundaries x equals 1 plus y minus 2 squared, and the line x equals 2. And first we're going to play with the graph x equals 1 plus y minus 2 squared. Well, we're going to be shifting 1 unit in the right direction, and we're going to be shifting 2 units, shift 2 units upwards. And that's because this is a variation of the basic graph x equals y squared, which is a sideways parabola with the vertex at the origin opening to the right. So we shift 1 unit up, 2 units to the right, and draw your graph. So that's what this thing's going to look like, x equals 1 plus parenthesis y minus 2 squared. So we're going to graph this. So here's our 2 on our x-axis. Here's our line, x equals 2, because that's part of the given graph. And then we have our point of intersection. Well, we haven't actually identified the points of intersection where the sideways parabola intersects the line x equals 2, but we are rotating about the x-axis. That means we're going to have an approximating rectangle parallel to the axis of rotation because we're using the shell method. The thickness is delta y, and delta y indicates that we're going to have a dy differential. Here we have x for the upper and I'm sorry, the leftmost and x for the rightmost, x as a function of y. So we have those two functions on the left and on the right, which all indicates the volume is going to be equal to y equals the lower c to the upper d value, 2 times pi times the width, which in this case, because we are rotating about the x-axis, is x as a function of y to the right minus x as a function of y to the left. And don't forget, y is the radius. I forgot to stick that in. I put it in now. It's 2 times pi times y times x right minus xl left, where the x's are expressed as functions of y. Now we need to find the points of intersection so we'll know how to integrate. So we're setting x equal to x to find y. So 1 plus parenthesis y minus 2 squared equals 2. Solve. Yes, takes the square root of both sides, plus or minus. It gives us two solutions. Y equals 2 plus 1, which is 3, or y equals 2 minus 1, which is 1. And then you can get the ordered pair for each of those y values by plugging them into the given equation. It's actually easiest to use the, since they're points of intersection with the line x equals 2, the y partners are both going to be equal to 2. So those are our 2 points. We can graph those 2 points of intersection with the line x equals 2. And now we can complete our volume. It's equal to the integral from y equal 1 to 3 of 2 pi times the radius y times the height 2 minus 1 plus y minus 2 squared dy. And that's 2 minus because it's x right minus x left. Now I'll let you finish that and post a comment if you or a question if there's anything more you want to discuss.